So, good morning, everyone. Today we're going to talk about exact equations. And we're also going to see an application by looking at population models. So, before I get started, does anybody have any questions on previous material? Or even on the homework, which is due tonight? Sure. Let's take a look. So the request is to discuss problem number 3. And problem number 3 is something like this. I would like to just identify the, we have solved an identical problem. I dare to say identical in class. Okay, so as I said before, always make sure that you do the problem from class a couple of times, but just to make sure that we're in the right path. Can anybody tell me what kind of equation we're looking at here? No, it's not a separable equation. But I didn't ask what it is not, I rather asked what it is. So what is it? It's a linear equation. It's a linear equation, and if you look at what we did last time, you will realize that I believe the one we solved was xy prime plus y is equal to x cubed, if I'm not mistaken. I mean, you can look it up, but it's precisely the same as that, right? I mean, the degrees are going to differ a little, but what do you need to do? You need to standardize it, and you can find this in the recording, right? Solved in detail. So what you need to do is standardize it. What do we mean by standardize it? We mean to divide by the coefficient of the derivative, and then you can find the integrating factor. How do you find the integrating factor? It will be, so this will be x prime plus 3 over t times x is equal to 1 over t squared. And now you need to find the integrating factor. How? By just taking e to the integral of 3 over t dt and apply the simplifications that we saw last time. So you're not trying to put any constants on the integrating factor. You try to keep it as simple as possible, and that's it. Okay, you're going to get a derivative on the right hand, on the left hand side, the derivative of the integrating factor times the soct for function, and then you're going to integrate the right hand side. Okay, are we good? So again, please study very carefully the problem that we solved on the previous class, and it is pretty much the same. Okay, are there any more questions, please, that I could address before going on? Okay, so so the kind of equation that I would like to study today is going to bring memories of conservative vector fields, because pretty much theoretically it's we're basing our approach on the same thing. So let me give you an example. Let me start with an example, and then we will see, first of all, why we cannot solve this equation in any other way. And also we're going to see how we solve it in the method that we're going to, according to the method that we're going to present. So please consider the following equation. y plus e to the x plus x minus sine of y times y prime is equal to 0. So consider this a differential equation. Okay, and let's see if this differential equation, the way it's given, if it's covered by anything that we have seen so far. Okay, so basically I'm looking to see if it is separable, and then if it's linear. So basically I'm saying it's not separable. Why isn't it separable? Because neither the quantity that you should take to the other side if you try to separate variables, or the quantity sitting in front of y prime, none of these two quantities can be expressed as a product of quantities in the respective variables. And for that reason, it's not separable. Okay? So you cannot really separate with multiplication the factors on these two quantities, right? So it's not separable. It's not linear. Can anybody tell me why it's not linear?
Is it because there's an e to the x in the equation?
The e to the x is not a problem, actually, if we consider the independent variable as x. E to the x is not really a problem. The problem, as it was noted in the comment that was just posted, is sine of y. Sine of y makes it as far from linear as anybody can ever get. So it's not linear, and so we have no way of solving it for the moment being. And we're going to introduce a new way of solving this. And to introduce the new way of solving this, I would like to also give you a kind of strange looking, but new way of rewriting this equation. So it might seem a little unusual, but here's what you do. You rewrite this as, and of course, please note that the first parenthesis is redundant, but in some sense, it helps us separate the two things. And then you once more treat the derivative in the Leibniz notation as a quotient of dy over dx, something which is really considered out of bounds at the first approach in calculus. But here at this level, you can do it, and you write it like this. And in general, when you bring a differential equation to this form, and allow me to call this P and this Q, my Q is not good. It looks like a mouse, computer mouse at that actually, but still, let's make it look like a Q. If we write it in this form, then pretty much what we mean by having an exact equation, so we're going to call this exact equations, is to have the derivative of P with respect to y being equal to the derivative of Q with respect to x. Then we call this an exact equation. Okay, then this is called an exact equation. And we're going to see today, one of the two things that we're going to study today is how to solve such equations. And, an interesting thing about these equations, there's going to be a slight difference from how we treated conservative vector fields in Calc 3. So with conservative vector fields, there was a point which I don't know how much you remember it or not, but it's an important point, that this condition that I like to call informally the compatibility condition is not sufficient in order to ensure that a vector field with components P and Q is conservative. Again, in fact, there are, quite, well, I don't want to say exotic examples, but there are examples of cases where the condition may be very well satisfied, but the vector field is not conservative. Okay. Here, in the case of differential equations, we have the luxury of not caring about any of this. So you may have a P and Q that would make the corresponding vector field not necessarily conservative, but in this case, as long as the compatibility condition is met, it's all that matters. And there's a very simple reason for that. That the compatibility condition, in the case of a vector field, ensures that the vector field is conservative in the vicinity of any point that you may choose. And that's all that we want here, because we usually have to deal with initial value problems. So we're interested in finding a solution around a certain point. Okay, so we have to ask ourselves now if the compatibility condition is met for the particular example that we have at hand. So, in other words, what is the derivative of P with respect to, so this is my P, right? And this is Q. And what is the derivative of P with respect to Y? It's equal to 1. What is the derivative of Q with respect to X? It's 1. So the compatibility condition is met. And what do? We find what we would have called in the case of vector fields, the potential. Okay, how do we find the potential? This is really the one place in this course where your whatever you remember from Calc 3 is going to be helpful. So the way to find it is you take the, no. It doesn't have to do with Green's theorem. I mean, yes, the difference of these two derivatives is something that appears in Green's theorem, but we're not going to be using Green's theorem here. So we just take the integral of P with respect to X, or you could take the integral of Q with respect to Y. So this will give you Y plus e to the X dx, which is yx plus e to the X. And let me see who remembers now Calc 3. What do I put here? What am I supposed to put here? Plus, not plus C. I'm integrating. So what do I put? No, it's not plus C. No. Well, yeah, you might say C sub Y plus G of Y plus G of Y. Very good. And now we're supposed to find Y. And how do we find Y? We make sure that by taking the partial derivative with respect to Y of what we just found, that we get Q. Okay, so this process will always give you something whose partial derivative with respect to X is P, but you also want the partial derivative with respect to Y to be Q. So for that, you will need to set this equal to X minus sine of Y, and this will give you X plus G prime of Y is equal to X minus sine of Y. And so again, we're totally looking back at what we did in the case of conservative vector fields. And this will give you G prime of Y is equal to negative sine of Y. And that means that G of Y is cosine of Y. So that means that the potential, if we consider this as a vector field, would have been yx plus e to the x plus cosine y. And now the idea is that the differential equation p dx plus q dy equal to 0 is really the same thing as saying that the differential of this is equal to 0. And if you have a function whose differential is equal to 0, at least locally, it's going to be constant. So pretty much what we need to do is take the potential function that we found, so yx plus e to the x plus cosine y, and make it equal to a constant. And that's your solution, which usually you expect to find a highly convoluted solution here. Now, there has been a question and a little change going on. So let me see if I can also, the phi at the beginning, yeah. So that was phi, and it was the letter for the function that represents the
Can you go back to the previous slide for a second?
I'm sorry, let me finish my phrase. It's the function that represents the potential, or what we would call the potential in this case. Yeah, let's go back, and that's it. Okay, so the method is precisely the same that we were using in order to find the differential, and then the potential, and then whatever you find that plays the role of the potential, you set it equal to a constant, and that's how it works. Okay. Questions, please. Why don't we do an example together? Okay, so allow me to now give you the differential equation. Now I will give you the differential equation in differential form, but please understand that if you're getting a differential equation in differential form, you should not assume right away that it's exact. Okay, so please don't jump to the conclusion that it's exact. You can literally take any equation and write it in this form, right? Any first degree equation where y prime is not, too convoluted. So please do not assume that it's going to be exact if it's given to you necessarily this way. But in any case, here, yes, what I'm going to give you is an exact equation. So y e to the xy plus ln of x dx plus 1 over y squared plus 1 plus x e to the xy dy is equal to 0. Again, you can divide the whole thing through by dx, and that's going to give you y prime on the right. Okay, so try to solve this equation. I'll give you a couple of minutes, and then we're going to solve it together. Okay, please go ahead. Okay, so let's do it together now. So as usual, we need to identify our P and Q. No, actually, let me start by discussing why it's not linear, why it's not separable, right? So why isn't it separable? It's something, it's a routine that you need to get accustomed to because you will need to do it all the time. So why isn't it separable? Because you cannot separate x from y in any of the two quantities sitting in front of dx or dy. So that's why you can't separate variables. Why isn't it linear? You have that y squared plus 1. That necessarily shreds any hope of having a linear equation here. So so we hope that it's exact, and we're going to find out once we check the compatibility condition. So we call this P and this Q. And what is the derivative of P with respect to Y? It's going to be e to the xy plus xy e to the xy. And what is the derivative of Q with respect to x? It's going to be e to the xy plus xy e to the xy, right? So that's precisely what it is. So it is an exact equation. And then we take, we try to find the potential for the corresponding vector field. If we want to use the language of potentials, then we need to talk about vector fields here. And what we're going to get is the is going to be the integral. Again, you can start with p of y e to the xy plus ln of x dx. So what are we going to get? You're going to get e to the xy. What is an antiderivative for ln of x? That's one of the reasons that I gave you the problem like this, so that we can all recall the antiderivative for ln of x. I remind you that an antiderivative for ln of x is x ln x minus x plus c. This is pretty much a very simple application of integration by parts. So, and please note it so that you remember it. And plus g of y, right? And then you would like the derivative with respect to y of e to the xy plus x ln x minus x plus g of y to coincide with q. You would like this to be 1 over y squared plus 1 plus x e to the xy. Okay, let's, I will need to change page, so let me give you a moment to catch up for everyone. Okay, and now let's go over to the other page, and we will have that x e to the xy plus g prime of y is equal to 1 over y squared plus 1 plus x e to the xy. This gives you that g prime of y is equal to 1 over y squared plus 1. Let me make the following comment here. It is of vital importance that what you get here has depends only on y. If you were to ask what happens if what you get here does not involve, involves also x, then the answer is that either you made a mistake with the integration before, or what you assumed that was an exact equation was not an exact equation. This is the point where you will always get stuck if you try to find a potential for a vector field which is not really conservative. Okay, but of course we don't have any problem here. G of y is going to be the integral of 1 over y squared plus 1 dy. And can anybody tell me what this integral is? Exactly, that's the arctan of y. And basically we will have that phi of xy is e to the xy plus x ln x minus x plus arctan of y. And please do not forget to write the solution of the differential equation. Here you just found the potential. That's not what you were supposed to find. You were supposed to find some equation that establishes dependence of y and x. So you need to write this as e to the xy plus x ln x minus x plus arctangent of y equals c, and that's your solution. And again, as you can see, this is a highly implicit solution. There's no way you can make this explicit. Okay, and this is what I warned you about in the very beginning, that yes, we would always want to have explicit solutions, but sometimes some methods, and especially this method of solving an exact equation, is not going to help us get an explicit solution. Okay, so we need to settle for an implicit solution here. Questions, please. That they're equal. So you find p sub y and q sub x, and you try to see whether they're equal or not. Okay, the question is what we're checking when we get p sub y and q sub x, and the answer is whether they're equal or not. Okay. Any more questions, please? Okay, so I would like us to take a quick break now, and when we come back, we're going to discuss an application of all this in the context of population models. Okay. I'm so sorry. So let me start over. We're going to, first of all, does anybody have any questions on what we discussed the previous hour? So we're going to talk about population models. As we said, in many instances in sciences, when we try to find a relation that tells us how a certain quantity works, we come up with a differential equation that we proceed to solve and then find the corresponding law, if you like, that tells us how things work. So this is the case with the study of how a given population evolves. And actually, the starting point of our discussion about this goes back to an incident that involved a scientist called Malthus. So Malthus pretty much suggested that the human population is increasing exponentially, and that the resources increase at a much lower rate, and eventually there will be starvation because of this inequality, of this discrepancy between population and resources. So to understand better his thesis, it's important to translate the exponential growth to a differential equation. So if we call, let's say, P of t the population at time t, then basically Malthus's law, which is going to be referred to as the Malthusian population model, is that the rate of change of the population should be analogous to the population. So this is a constant k, the proportionality constant. And please understand that in any particular instance, this constant is not a priori known. And in order to determine it, you will need to have data from 2 years. So when you try to solve such a problem, I mean, it's fairly easy to find the solution. So this is a separable equation. So you will have dp over dt is equal to k dt. This is an equation that we solved from the very first day. So you will have ln of absolute value of p is equal to, sorry, I'm taking the integrals, and I have ln of absolute value of p is equal to kt plus c. And then I hope you all remember what we did here. We said that the absolute value of p is equal to e to the kt times e to the c. And we said that to make our life easier, just replace e to the c by c and think of it as a positive constant. And here we're talking about population, so it does have to be a positive constant. And then p is going to be plus or minus c e to the kt. And we allow c now to be non-zero. And then we notice that c equals 0 also works. And finally, we come up with this equation. And here at this point, you can see that this c, if you set t equals 0, you will realize that p of 0 is exactly c. So sometimes we like to write this as p of t is equal to p naught population at time 0 times e to the kt. And I suggested a moment ago that you need to know the population at time t at 2 times. And usually what happens is you have a year for which you start your considerations, and you call that year 0. And then you try to figure out what the constant k is by having information for another year. So let's consider a particular example so that we see how this whole thing works. So let's suppose that we have that p of 0. So let's say that the population of a town was 10,000 in 2010. 10,123 in 2015. And we're asking how much is it today? So how does this work? We said that in general, the solution is given by this, right? And P naught in our case, so year 0 in our case will be, we said as year 0 to be 2010, which means that 2015 is going to be year 5. And 2023 is going to be t equals 13. So far, so good. So P of t is going to be the population at time 0. So this is going to be 10,000 times e to the kt. And now we want to find how much k is, right? So what do? We put P of 5, which on the one hand is known to be 10,123. And on the other hand, it's known to be 10,000 e to the kt, e to the k times 5, I'm sorry. So now you have this equation and you're supposed to isolate k. Let's see how it's done. So we have 10,123 is equal to 10,000 times e to the 5k. If you take the logarithms of both, I mean, maybe you need to divide first by 10,000 is equal to e to the 5k. And I hope you can see how this works. So this gives you on the left 1.0123. And you have e to the 5k. Now you take the logarithms of both sides. And ln of e to the 5k is simply 5k. And eventually you have that k is equal to 1/5 ln of 1.0123. Okay, I'm not going to ask you to do any explicit calculations with this, so you don't need to have a calculator in order to find ln of 1.0123. But if we wanted to make our life easier, not really make our life easier, if we wanted to make a computation, then let's see how much this is. So I'm using actually my browser right now. We live in an era where Google can do all the computations for us. And this turns out to be 0.00244. Let's say I'm trying to keep as many digits so as to make this as meaningful as possible. And we get P of t is equal to, so k is equal to 0.00244. Okay, and this will end up being 10,000 e to the 0.00244 times t, right? And this is the population according to the Malthusian model for this specific instance. And so if we want to find the population for the year 13, which is supposedly our year 2023, this will be 10,000 times e to the 0.00244 times 5. Okay, let's see if I can compute this real quick. So let's see how much this will.
Wait, why is it times 5?
I'm sorry, it's times 13. Sorry about this. Thank you for catching this. And what I found is 10,322. I'm rounding it, of course. And that's what the population model projects that or suggests. Usually you're going to see that the Malthusian model is good enough for small periods of time. If you try to use it for larger periods of time, then you're getting really ridiculous results, which suggests that why such models, why Malthus's thesis was not exactly correct. So I would like to give you an idea by, okay, so let's see what the US population was in, let's do a quick computation, right? So let's play with the US population. So at 1800, the US population was 5,308,000. And then let's see what the US population was in 1810. So in 1810, the population was 7,239,000. I'm rounding to the thousands here. So let's apply our model, right? So if you solve everything the way that you did before, you would have that the quotient of these two things, which is this much. So I'm trying to find K now. Would have been 1/10 times, or rather, K would have been, yeah, this is a better way to write it. I can take the formula that I found before. So K would have been 1/10 times ln of this, right? So let's see how much ln of this is. So my year zero now is 1800. So I have ln of this quotient. And I found 0.031. Okay, 0.2, let's say. Let's keep it as precise as possible. So now, if I wanted, according to the Malthusian model, to compute the population in 2023, that would be 223 years later, right? So this would be the population in the year 1800 times e to the 0.03102 times 223, right? Allow me to compute this and see how much this population model suggests that the population of the US is right now. And let's see how realistic this is.
والله كتير confusion هذا الكلاس.
Yes.
عامل لي كتير.
Please mute yourselves. I'm sorry. So here's the number that I found. Okay, so here's the number. This is it. Let's parse it. Okay, let's see what this number says. 5 billion people, 5.5 billion people. That's what Malthus's model suggests for the US for today. And you all know very well that there are not 5 billion people in the US. You all know that, right? So, so you might say, so is this model completely useless? And like I said before, no, it's not useless. It's useful for small periods of time. But if you try to see what happens over such a huge period of time, especially when you had such a huge increase, I mean, if you look from 1800 to 1810, the increase in the population, that's a huge increase. Okay, so this rate is unsustainable. But if it was possible, then the US would have had population of 5 billion. Of course, you have to understand that here there are other factors. So you have immigration. You don't have just people who are born within the confines of the US. But that's exactly what these population models cannot predict. They cannot predict acts of God. They cannot predict consequences thereof. So if you have, let's say, a wave of refugees, that is not going to be predicted by any population model, no matter how good it is. However, people try to improve on these population models, and they came up with a different model, which is more precise for a longer period of time. But once more, if you try to apply it for a longer period of time, then it's going to be pretty much as useless as the Malthusian model. It's called the logistic model. So in the logistic model, you take dp over dt, and you set it proportional at first to the population, but then you subtract a factor, you subtract a summand whose goal is to take into consideration all deaths that are attributed to human interaction. And human interaction, each person interacts with the rest of the population. The rest of the population is p minus 1. And that's why this is the differential equation for the logistic model. It's again a separable equation. I'm not going to solve it. Obviously, it's much more involved than the Malthusian equation. But if you solve this equation, and your book actually does have the solution, but I'm not going to require you to go into the logistic equation, then you can find a solution that again can predict the population much more precisely than the Malthusian equation. But again, it's going to be almost impossible to use it for longer periods of time. And like we said, none of these mathematical models predicts special events that can happen. Okay. Yes, you had a question?
Yeah, so the first one just predicts the population based off of, nobody kind of dying, but the second one the logistic model puts into consideration people's death.
No, it's not precise to say that nobody dies, because when we did the very first example, and we said that the population went from 10,000 to 10,123. That doesn't mean that nobody died. Some people died and some people were born. Okay, the main premise of the first model is that the rate of change is proportional to the population, which is to say that we have an exponential increase. That's the premise. Okay, the premise is not really about the population, the inner workings of the population. It's about the rate of change of the population, and that's how you form differential equations. So in the second case, you refine the rate of change and you take into consideration deaths that are attributed to human interaction. But as we said, none of these equations can predict things that happen in a macro scale, and immigrations or waves of refugees or wars. I mean, you can have a model that could work fine before 1940, and then once the World War happens, this model is out of the window pretty much. Okay. The other thing that I want you to understand is that when we say that we study population models, this study can carry over right away to the case of other types of species, let's say. So you can study over much smaller periods of time bacteria, viruses, or other live beings. Or it can even be applied to a completely different setup. And that's the nice thing about studying such a problem, that you just keep the math, you just keep the attributes of the particular problem. And if you can apply them in a different situation, then the solution can be used in that case. I would like to wrap up our class today by taking the attendance. And, let's all remember the name of this fellow that we just discussed. So please send me Malthus as the keyword for today's attendance. Okay, are there any questions, please? Let me also take a very quick look at the homework and make sure that you're not going to find something quite exotic here. So we have two exact equations for you. The one of them comes with an initial value problem. And then we have a Malthusian model for a small town to predict what the population is going to be. Now, for the Malthusian model, I want you to understand that I don't want you to do this whole thing here. Okay, Hamza, as we said, this is a little late. Okay, so please always submit the keyword within the 30 seconds. But anyhow, you can always jump to this. So when we discuss the Malthusian model, you can begin with this as your starting point. Okay, so you don't need to show how the equation is derived. Okay, does anybody have any questions? Alejandra, it's the same remark that I made to Hamza. So please submit the keyword within 30 seconds. Otherwise, I cannot give you the attendance for the specific class. Okay, please be on alert about the attendance. I wish everybody a very nice. It's okay. I mean, one and now we have Fidel and Aya. So everybody, let me repeat it. The attendance needs to be given swiftly within 30 seconds of when I give you the keyword. So the last 4 of you who gave me the attendance right now, it cannot count. It's okay if you miss one class or 2, but please always stay with me. Okay? Okay, excellent. So I hope you all have a great day. Please review your the recording when it becomes available, redo the problems, and then try your homework. And I'll see you on Friday. Have a great day. The quiz on Friday, it will be an exact equation. It will not be Malthus, it will be an exact equation. Okay?